Hi there. So today in this lecture we're going to continue our discussion of spatial joins. We're going to look at a few more complex examples. And in particular we're going to look at different predicates or spatial relationships beyond the intersects that we used in the previous lecture. And we're also going to do more troubleshooting because, hey, you're always going to run into problems that you need to troubleshoot doing this type of data wrangling work. Well, we used intersects in the previous lecture, and this is one of the most common spatial predicates. In other words, the relationship between geometries, points, polygons, lines. And it's great if you want to know if, say, a point is within a polygon or on the boundary of a polygon, or if two lines cross. But sometimes we want to use different spatial relationships or predicates. So I'm going to start. This is the same code as we did before in the previous lecture. We're going to load in our libraries. We're going to read a food pantry data set. We're going to create a geodata frame and reproject it using our points from XY function. And we're going to import the census data on median incomes. Now let's have a look at what predicates are available to us. Well, these are defined in the Shapely documentation. So we have some examples: contains, equals, intersects, covers, covered by, crosses. In most cases, there's a plain English interpretation of these. Overlaps, that is pretty obvious, or touches, that's pretty obvious. And so which one you choose is going to be guided by the task you're doing. Now this is Shapely documentation. We're not using Shapely directly, but Shapely is a library that's working behind the scenes for many of the functions that GeoPandas has available. And here are some of the valid query predicates that we could use. It's a subset of these that are in Shapely that GeoPandas recognizes. So let's try three of these different ones: intersects, contains, and within. So we're going to start by printing how many pantries and census tracts we are. And then how many rows are we going to get if we do the same spatial join that we did in the previous lecture? We're going to use GPD join between a subset of our income data frame columns and our pantry data frames. We're going to do an injoin, and we're going to use intersects. And this is exactly the same, but rather than use intersects, we're going to use contains. So does our census tract contain a pantry? And then the third one we're going to do is within, is a census tract within a pantry. So intersects and contains give us exactly the same result. And there's 209 that are intersects. There's also 209 census tracts that contain a pantry. But there are 0 census tracts that are within a pantry, which makes sense. Right? A census tract, which is a polygon, can't be within a point, which is in a pantry. It's just too big. Also note that we have fewer join results than pantries. We only get 209 rows here, but we might have expected to get 211. Why is that the case? Well, perhaps some of our pantries are physically outside the county, even though back here we already asked GeoPandas to limit to the pantries that are in Los Angeles County, but maybe we made a mistake. So we need to pause the video and think, how would you verify this? If this is your hypothesis that our join is failing here, we're losing 2 pantries because they're outside Los Angeles, how would you verify that? Well, the first thing I do is to look at the county field in the pantries data set. So let's group by county and ask for the number of rows in each county. Well, 211. That's not a surprise because we asked to restrict the data set to Los Angeles County in the first place, but hey, we could have made a mistake or something else could have gone wrong that we weren't expecting. So either all the pantries are within the county, or there's an error in a county column, maybe we're missing some census tracts, or a join is going wrong. What else could be the case? With these types of spatial joins, a good troubleshooting step is to map things. So let's map it and take a look. So we're going to import our matplotlib and contextually libraries. I'm going to create a blank figure. Now let's plot our pantries. Let's also plot our census tracts. We're going to plot them at 50% alpha. This is 50% transparency or opacity, and this is good if you want a layer to be a little in the background. And we're going to do the same for our base map. We're going to have it at 30% opacity so it appears in the background. Okay, so these are our census tracts for Los Angeles, and it looks like we see the problem here, right? We have these two pantries which seem like they are outside the counties. So probably there's an error in some of the data in the county field, or perhaps lat long coordinates are imprecise. So how do we find the culprits here? Well, a good function here is difference. This works on columns. It also works in a pandas index. And this is what's called a set theoretic operations. So difference is looking for the elements that are in one set, in other words, an index in this case, but not the other. And we can read about the difference here. If we're applying it to an index, it returns a new index with elements of this index that are not in this other. So what happens here? Okay, we got more than two. We should expect two rows because we had 211 in pantry geodata frame, and we had 209 that we got back in our intersection. We're looking for these two culprits. Well, let's have a look. Okay, now we see the issue that we have an integer index rather than geo-ID. Our original index is actually in this column called index right. So rather than do the difference from this index based on the index of pantries intersect, let's do the difference between our original index and this index right. Okay, this looks more promising. We get two rows. What are these rows? Well, let's pass them to our lock operator that we saw before. Before we just passed one, but we can also pass two as a list. Okay, and even though the county field says they're in Los Angeles, we can actually see from the cities that these are actually cities that aren't in Los Angeles County. Upland actually is in San Bernardino County, and Los Alamitos is in Orange County. So we can ignore these. We don't have to worry about these two quote-unquote missing pantries. We'll work with the 209 pantries that were spatially joined. So the overall point here is that spatial joins often throw up unexpected results, and you'll have to do the type of detective work that we just did to figure out what went wrong. GeoPandas also provides some useful spatial attributes. Areas, lengths, bounding boxes are just three examples. Now, when we were doing spatial joins, we didn't really have to worry about the projection. As long as both data frames were in the same projection, it didn't matter what that was. But when we're looking at, say, distances or areas, that does matter. You probably don't want to measure distances in degrees. It's really meaningless. But even a projection in meters can be distorted. So the best projection for measuring distances and areas, sometimes you can use a global, like an equal area or an equidistant projection. In the United States, the state plane coordinate systems are usually the best choice for local level work if you're working for a particular county or region. And Los Angeles happens to be in the state plane zone, California 5. We can see some information about it in the EPSG website. It gives us the definition and some of the use cases. So the area of use is in Los Angeles, Kern, San Bernardino counties, and so on. And it has an EPSG code of 3497. Now these units are in meters. If you want feet, you might want to do 6424, which for units are in US survey foot. This is the EPSG website. Spatialreference.org is another one that gives similar information. So let's look and see what this difference this makes. So we're confirming that our projection is 3857. Again, this is Web Mercator. And what are our areas of our census tracts for the first 5 rows? Well, what if we convert this to the California state plane in meters? So when Mercator is in meters, it has a lot of distortions at the local level. So we're actually quite different, exactly different results. And the area of a census tract depends on the projection. When Mercator is crummy in this instance, we should be using state plane or an equal area projection for a larger area. What's the length attribute? Well, our census tracts are polygons, So a length isn't the length of the line. In this case, it's the length of the perimeter. We're in meters, so we can see that this census tract 0 has 14.5 kilometer length. And if we want to know what census tract this is, let's just set the index to the GeoID, and then we get the length of the perimeter for these different census tracts. The projection is less important for the bounding box as long as you know which one you're using. So let's get the bounds of this geometry. This is a rectangle that is the smallest rectangle that contains the geometry. When they cater, these coordinates are less meaningful than they might be as if you're converting it to lat long, 4326, and then looking at the boundaries. So this is sometimes more interpretable if you want to, say, cross-reference this with a map or in Google Maps to see what area you're looking at. So the takeaways here: while intersects is the most common spatial predicate, it's not always what you want. Sometimes you want crosses, sometimes you want touches, sometimes you want contains. The projection matters, and probably 90% of the times you get an error in a spatial join, it's because your projection is messed up, or it's not projected, or not defined, or it's not what you're expecting. So as with any join, look at your output. And if it's not what you expect, compute these summary statistics or map in the same way as we did in this lecture. That can help identify the problem.